Okay, thank you very much. And apologies if I get off to a little bit of a rough start, but hopefully things will smooth out as I get into the talk. Okay. So let me just find my screen share button here. Okay, are we good?
Yep, looks good.
Okay. So yeah, basically this is my story of prop.kc2g.com, where it came from, how it works, what its future might possibly be. As you see, I'm Andrew, KC2G, member of YCCC, also Fair Lawn Amateur Radio Club down here in New Jersey. Slides will be available. You don't have to copy this down right now. I'll make sure that it gets to the mailing list as well. And as you've all been informed, this talk is being recorded, so that should be available somewhere as well. Just a little bit of background on me. I'm a relatively new ham. I got my license the end of 2017, upgraded early 2018. I have a medium-ish station down in northern New Jersey, a little over half an acre, got a flex, got a 160-meter loop up in the trees, and a hex beam, and some various VHF, UHF stuff. I do mostly a little bit of SSB contesting, CQ WPX, CQ WW, 160, etc. I also like to go portable, play around with digital. Didn't mean to do that, sorry. Play around with digital stuff, do the VHF contests, etc. And I write software professionally and sometimes non-professionally. So what prop.kc2g.com really is, it's a website for amateurs to go to and get information about what HF propagation conditions look like right now. It is entirely open source. You can find the source on GitHub. It's built from lots of open source components, lots of libraries, Python, NumPy, Matplotlib, George, IRI model, etc. It is written as a bunch of separate communicating services written in a variety of different languages, just based on convenience and based on things that already existed. Stores stuff in Postgres database, has a REST API. Anybody can use this thing. So how did it come to be? Like I said, I'm only been a ham for 3 and change years. Got on HF early in 2018, and I was looking for information like how do I know what bands I should be using? How do I know where am I going to be able to talk to? And of course, you can turn on the radio and spin the dial and see what happens. But I wanted to understand a little bit more. And I found a variety of sites that had maps of MUF, and a lot of them were really kind of challenging to read because some of them are literally 640 by 480 16 colors. And I know that was technologically impressive at some point, but very difficult to read information off of that. And I found another site that was created by Matt Smith, AF7TI, that was graphically much nicer than a lot of these. And I went to it on a daily basis just to check things out. And then it disappeared after a while because he just runs a bunch of experiments on the web, and he puts stuff up and he takes stuff down and changes it around. And so it was gone, and I was sad. And then I happened to find his source code on GitHub. So I said, okay, I'm going to take this. Let me see if I can get it up and running on my server. Changed a couple things around. I got it running. Okay, now I can look at these maps again. And I realized, oh, there's things I could actually improve about this, because like the interpolation algorithm that it uses doesn't give the same values at -180 longitude and +180 longitude, but those are the same place. So why shouldn't they have the same values? And I fell into a gigantic rabbit hole of learning how this thing worked and seeing what I could do to it. So everything that I have comes from a starting point of AF7TI's muff map, but probably 90% of what's there has either been written or rewritten by me by this point. So the functionality that it provides mostly is you go to the page and you'll be able to click muff or FOF2 and see the maximum usable frequency or the critical frequency for anywhere in the world right now. There's also a page that has a cool graph of effective sunspot number or effective solar flux, depending on, how you want to look at that. There's actually a bunch more stuff in the back end that's not quite ready for public consumption. We'll get into that as the talk goes on. One big caveat is it is entirely based on F-layer HF prop. It doesn't, at this point, know anything about the E-layer, sporadic E, tropo, any other kinds of things. So a little bit simplistic in that fashion, but it does one thing and does it relatively well. So if you want to know how it works, it's worth starting with a little bit of honesty, which is that the data that I have to work with, the ionosphere is very actually lumpy. It's not a big smooth thing. There's a lot of variation in time and space. It's a bunch of clouds of gas that are moving around all the time. And we don't have the kind of data that it would take to really map that accurately. So what you're seeing is mostly guesses. If you're looking at the present, it's guesses. If you're looking for the future, it's wild guesses. But we'll try to make the best guesses that we can, maybe make slightly better guesses than other people. And so in order to do that, we take information from ionosons, which is basically take a radar, an HF radar, point it straight up, send a signal into the sky at a certain frequency, and measure the signal you get back and the delay of that signal coming back. And so then you can find out what height is a given frequency reflected from. And they give relatively up-to-date data from the real world. But if you look at a map of where ionosons actually are, first off, there's not a ton of them to start with. There's like 100 in the public database that have reported ever, and maybe 50 that are currently reporting on a regular basis. US is full of them, Western Europe is full of them, basically everywhere on the coast of Australia has one. But there's also big dead zones. Oceans are empty. Africa has basically nothing except for South Africa. Russia and China have them, but they're not telling the rest of the world about what measurements they're making. There's some coverage around the poles. Canada has some high Arctic stuff, and there's a few in Antarctica, but it's not enough for any kind of detailed coverage. The ones that we have are, they measure on different timescales. They take different amounts of time to report their data, and all measurements are noisy. All measurements are subject to problems with interference and sporadic E-clouds getting in the way and whatever. So you're not going to get 100, even in the places where you have these measurements, they're not 100% reliable or noise-free. So the AF7TI system was based purely on taking ionoson measurements and just kind of averaging out between them. And it was cool, not actually terribly accurate as I came to understand. The other resource that we can use is computer models. IRI 2016, International Reference Ionosphere, is a relatively well-known one. It's what they call an empirical model. So they took decades of scientific measurements and compile it all into tables and write algorithms that will replicate the average of those measurements as well as possible. So you can run this model for any time in the world, any place in the world, any time of day, any time of year, etc. And it will give you back numbers for you know, critical frequency, muff, height of the F layer, etc. But they're climate, not weather. You give it this, you ask it the same question, it'll give you the same answer every single time. It's like asking, what is the high temperature going to be in New York on the 4th of July? You can look that up in the almanac and you're going to get the same answer every time. If you've used software that gives you a propagation prediction and it just has you say, you know, what's the time and what's the smooth sunspot number, that's a tongue twister, then it's based on this kind of a model. So both of these things have their pros and their cons, but what would be really nice is if we could combine the two in a nice kind of way. My definition of a nice kind of way is if you have observations, then your model should give values that are close to those observed values when you are close to the observations. If you are far away from any known measurements, then you should be consistent with the observations you have and with the model at the same time. And you should be plausible in the way that things vary, which means that, you know, if you have some measurements over in North America, you have some measurements over in Europe, then the Atlantic Ocean should not just be kind of a featureless void. We know things about the way that the ionosphere works. The IRI model captures those things. So we should be able to make a guess about what's going on there, even though we're not measuring there. And there should be no sudden jumps because the real world is relatively continuous. The approach that we take to do that is get our observations from the ionosons, store them in a database as they come in, use the recent history of those observations to back out the model formulas, because the IRI model has formulas that say, for a given solar flux, this is the critical frequency that we should observe in a given place and time. So we have a bunch of observations from a given place and time. So run a numerical optimizer on that says, what value can I give to the model that will, for solar flux, that is most consistent with all of the observations that we've seen. Use that number, feed it into the model to make a baseline prediction of a map of all around the world. What are things like? Then for each ionoson that we have, look at its recent history, do some extrapolation to the current time and even some hours into the future. And look at that in a way of difference from climate. So how far above or below the measurements are the observations for this location, and then combine those spatially. And I'll go into a little more detail on that. But first, our data sources, there's two that we have. The first is NOAA, National Centers for Environmental Information. So they push, I have a push feed from them, so they just send me the observations as quickly as possible in SAO format, which is basically the raw observations from the ionosons, and I have a loader. And Global Ionospheric Radio Observatory, they have an API. So this is a script that was written by AF7TI that pulls their API every 15 minutes and says, what new information do you have for me? Pulls them down. In both cases, the data that I get from them is the location of the ionoson, the date and time of an observation, and a bunch of things like critical frequency, height of the F layer, muff, and it varies from station to station what information they're giving me, but those are the top three. Sometimes you also get back a confidence score that says, This is a good measurement from this station. This is a bad measurement. Don't trust it. Sometimes you don't. So given all of that, I compute an effective solar flux. There is a site, Northwest Research Associates, that has been doing something similar for, I think, like 30 years. So what I'm doing is similar to what they're doing, but I made a few changes. But so take the past 25 hours of observations from all of the stations, do some weighting, do some filtering and windowing. And as I was saying before, optimize that one critical parameter of the IRI model to find the value that gives the best agreement with all of the observations over the past day. And then from then on, tell the IRI model, this is the solar flux value that you're going to use. So instead of loading it from the file that says, we're this far into solar cycle 25, therefore I expect the sunspot number to be blah, it's just going to be based on that. So that's a baseline that is somewhere kind of calibrated with reality. Then for every ionosonde, look at the past 2 weeks of data that we have, and compare every observation with what the IRI model would have predicted using our effective solar flux. And we look at the differences in log space, which works out kind of nicely because for one thing, it's scale independent. So you know, critical frequency has a range of a few megahertz. MUF has a range of more megahertz than that. Height of the F layer has a range of hundreds of kilometers. But if you take the log of all of them, then they have basically the same range of variation. And now the difference between being 400 kilometers or 10 megahertz is just a constant difference. And since we're subtracting out the mean anyway, it's nice. Also, working in log space means that your interpolation will never give you a negative value. It will never say that the MUF is -3 megahertz, which is convenient because the MUF never is -3 megahertz. So we take all of those measurements, we throw them into a model using something called Gaussian Process Regression, which I'll tell you more about, and get the values out for the current time and for 1, 2, 3, all the way up to 24 hours in the future. Now is still a prediction because the data that we have from any given station ranges from, say, 15 minutes old to a couple of hours old. So we want to align all of those to the same time, which is now, which is somewhat in the future for all of them. So even when we're not looking at, you know, tomorrow, it's still basically a prediction. Store that stuff back into the database. And it's a really important point that when we're doing this, we're only asking the model to deal with the difference between observations and the IRI model, which means that the capacity of this model doesn't have to be high. We're not asking it to understand everything about how the ionosphere works. We're not asking it to understand gray line and day versus night and how all of these patterns work. We're only asking it, you know, if it's high now, is it going to be high in a few hours? If it's low now, is it going to be low in a few hours? Make your best guess. And that carries through the whole thing. We have a model that knows about ionospheric behavior, so we're not trying to duplicate that knowledge into another model. What Gaussian process regression is a really pretty cool statistical technique. I can't give a full mathematical explanation of it, but it's a generalization of a lot of least squares type curve fitting techniques that are out there, except that what you do is you give it a covariance kernel, which sounds pretty complicated, but basically it's saying for given two different observations, how strongly related is the difference from the mean of one to the difference from the mean of the other. And that captures a lot of things, including how smooth or how rough you want the output to be, and whether it's periodic, etc. So for the kernel that we have for time prediction, we're saying, well, right now is going to be pretty similar to 5 minutes ago. Not much changes most of the time in 5 minutes. 15 minutes ago is also similar, but not quite as much. 30 minutes is also similar, but not quite as much. So that's going to generally go down the time. But now is 24 hours ago is going to be a lot more similar to now than 13 hours ago. And 48 hours ago is going to be similar to 24 hours ago, but a little bit less, etc. It's a great model for dealing with time series that have irregular time steps or missing data. It doesn't have to be running in lockstep. You don't have to, feed it dummy values to fill in the blanks. And if you give it values that have uncertainties, like those confidence values from the ionosons, you can get uncertainties back out. So I did my best to fit a kernel to a year of the observations that I have. And it looks something like this. As I was saying on the previous slide, you have the scale there is hours. So, an hour on either side of an observation is pretty well correlated, and as it drops down and you get down to 4 or 5 hours away, and it's not going to be very much. There's this little hump at 12 hours, which is interesting that you actually have kind of a semi-diurnal pattern there. And then at 24 hours, it starts rising back up. If you look at the longer term, you can see that actually over the course of, this is plus or minus 5 days, but over the course of a week, there's still a fairly strong correlation. So we can use this. And this is one of my internal debugging tools, and this is observations with error bars are in the blue, and then the predictive output of the model in the orange, and you can see it doing a reasonable job of guessing what is going to happen tomorrow or today, since I made these images yesterday. Here's another interesting case where this was taken from Idaho, which stopped reporting data or had a lag in reporting the data. So you can see that there's a 10-hour gap where we don't have data for the past 10 hours, but we can still start predicting at the current time. And it's just going to be based on a combination of the latest things that we've seen and the 24-hour-old data, with a little more uncertainty, which you can kind of actually see that those error bars are wide. So that's the first major step in the system, is for every location, do that prediction in time. The second step is very similar, only different. So for the time that we want to make the map for, which we'll say it's right now, look at all of the ionosons that we have, filter out the ones that haven't had an observation in too long or their confidence scores are too low. Convert their latitude, longitude coordinates to XYZ coordinates in 3D space, and do another Gaussian process regression in 3 dimensions. This time, the kernel is just a simple function that says the further apart you are, the less related they are, which makes for a pretty simple interpolation technique that goes by a lot of names, and is basically found in every kind of geospatial software. And then we can query that model for every point of latitude and longitude. So this is a map of critical frequency difference from model for sometime yesterday, we don't have, you know, the landmass map or the political map underneath it. So you have to kind of imagine it. But, you know, the Western hemisphere is on the left, Eastern hemisphere is on the right, north is up, south is down, etc. And you can see the range of, there's an area where it's minus a couple of megahertz, and there's an area where it's like plus 1 megahertz from our best guess model. So all of this gets applied into the map. So basically we take the numbers that came out of the IRI model, we add these numbers into it, store that back into the database as an HDF5 file, and make our pretty maps with labels and dots and all of that stuff. Underlying libraries include matplotlib, which is a really super capable Python graphics library, and CartoPy, which goes along with that and handles maps and base maps, so drawing the land masses. It also has the ability to compute the subposition and draw the gray line, and do map projections. And this is the part that AF7TI did an awful lot of hard work on that I couldn't have replicated myself. I did some refactoring to it to make it a little bit more manageable, but my maps still look very similar to his. And this is a slightly modified one with the grid lines removed to make it easier to look at. But so the dots represent recent observations from the different ionosons. This one is a map of MUF, as you can guess from the range of the numbers. And then the shading and the contour lines represent the position, the predictions. And you can kind of look around here and see my earlier point about where the locations are. North America is doing good. South America is doing pretty good. Western Europe is good. Eastern Europe and a lot of Asia are kind of a black hole. Oceans are pretty empty, but then Australia is doing good. So this is the basic thing that you can go to the site and look at and say, you know, how high is the MUF getting? What direction should I be able to get out in? What bands should I expect to be open? It takes a little bit of knowledge to use a map like that, but it's knowledge that's been spread around for a lot of years because these kind of maps have been available for a long time, and this is just a slightly more real-time advanced version of those maps instead of getting one from a book. A quick note about how the different parameters are modeled. So critical frequency is modeled directly from the IRI model and the observations. Does exactly the things that I was saying in the previous slides. Height of the F layer is also modeled directly. There's no F layer height map on my site, but it's generated and it's used for some other things. When we're doing MUF, instead of doing it directly, we take, we take for any ionoson that gives a MUF, we divide MUF by critical frequency to get what's called the M factor. We can get the same parameter from the IRI model and then do all of the smoothing stuff on that, and then multiply the smoothed out M factor by the smoothed out critical frequency, which all sounds very involved. But the benefit of that is that there are more ionosons that give us critical frequency than there are ones that give us MUF or M factor. So by doing it this way, we can use the higher resolution data for critical frequency to contribute to the MUF map. It's a small difference, but it's one that hopefully does something useful. And so basically those maps and the graph of effective SFI over time are everything that you can just go to the site and click on right now. But there's other stuff. There's other stuff that I've been working on for literally years at this point, that is not quite available. So the first one is maps for the next 24 hours. Those are actually being generated right now. They're on the site, like the files are uploaded. There's just no way to get to them. And that is based on lack of time / lack of web dev skills to actually create a way to navigate to those. So for that, I apologize, but it's actually possible right now to just basically edit the image file name and say 6H instead of now, and it will give you a map for 6 hours into the future. The second category is things based on ray tracing. If anybody has ever been to the vocap website or Propy website, which I can highly recommend, they have a bunch of tools where you can put in your location and get maps of, excuse me, maps of the highest and lowest usable frequencies from your station to anywhere in the world at a given time. Or put in your location and another location, and it will give you a forecast of what bands will be open when between those two locations. In order to do that, you need a ray tracing engine that takes those maps and uses them to actually basically model the communication path between point A and point B. Say, given this ionosphere, is the signal going to make it or not? And so I went and I did that using one that I could find, which was Muffwin, written by K1TTT. And it works and I can get things out of it, but the results are not quite up to snuff. But I will show you, I'll show you some of what that can do. Anyhow, more recently, I found that the source is in fact available for ITUR-HF-PRA, which is a mouthful, and that it is written in C, not impossible to comprehend. Fortran, I'm not saying all Fortran is bad, but if you look at things like vocap or IcePack or Minimuff, etc., they are some of the absolute toughest to comprehend code that I have ever seen. But ITUR is actually modular and easy to deal with. It seems to require for its predictions exactly the variables that my model can already deal with. Integrating that in, like basically cutting out the pieces of it that I need and replacing its internal ionospheric models with, hey, just get the data that I have, is possible, but pretty labor intensive. And yeah, I have a job, I have a house to take care of, I have an 8-month-old baby. So someday I hope to be able to integrate that. And even once the backend work is done, you need an interface to be able to do the stuff that those sites do, to be able to select your location and navigate between the different stuff and display all of those graphs. So for now, I'm sorry, you just get a tease, but this is an example of set a station location, I think, in the UK, and say, all right, you know, what bands are open to where at a given time, which was sometime in March, so not super impressive. And it would be able to tell you that. Obviously, it's showing you the gray line as well. If you see the crosshatch areas down between Australia and Antarctica, that's the model saying, I think that you would be best off using long path to get to this location. So all of that is possible. It just needs a whole lot of work, but it's a future direction that I'm very much hoping to be able to take. And this is very rough proof of concept of a point-to-point prediction of you know, what bands can I use at what times to reach this location, this station from my station. Again, needs a lot of work, but just to show off that it's something that I've been playing with, and this is entirely a free time project for me. Getting into more kind of crazy developments. So I explained that the Gaussian process prediction components first do it for every location in time. Then once you have time alignment, do all of those in space, which is three-dimensional. That's actually not making the best possible use of information. What if we could actually just throw all of those into one pot, one four-dimensional pot, space and time, and say, okay, given that it was like this here at this time and like this here at this time, et cetera, then what will it be like here at some other time? And that is entirely possible using Gaussian process regression. It would also have the advantage of being able to take into account the fact that the Earth rotates, so a lot of this is going to be correlated. The conditions here now are going to be similar to the conditions 15 degrees east of here an hour ago. But that's throwing a lot of data into the model at once, and the algorithm scales with the cube of the number of data points that you put into it, which is tough. So it either needs more hardware thrown at it or it needs smarter algorithms. I've read about some algorithms. KISS-JP is kernel interpolation scaled something Gaussian process. I forget. You can look it up. But this is a very interesting idea that I may or may not ever have time to get into. But I don't know. I always have the hope that someday there will be someone who understands far more about this stuff than I do that wants to come and help me. Which, yeah, that's tough. But like, I seriously have come into this from a point of basically no knowledge and bootstrapped everything myself. So I'm very much willing for anybody to give me a little bit of help. And lastly, so something in CT1BOH's presentation, he was showing, well, can't you just do this based on the spots for PSK reporter for a given band? Because with so many people using FT8, FT4, et cetera, you have this just fire hose of information coming in of what is reachable from where on what frequency. And you should be able to use that for real-time propagation maps, and you should. But that's harder than it sounds. First off, you have a very basic informational problem, which is if you get a spot from point A to point B, then barring data errors, that means that there is prop from point A to point B. If you don't get a spot from point A to point B, that doesn't mean that there's no prop. It might be that there's nobody listening in point B. It might be that whoever's listening is on another frequency. It might be that they have QRM or the antenna is pointed the wrong way, et cetera. And you also have to be careful about how you actually factor in the distance between two stations. And the bigger problem than that is that most of the world doesn't get enough data to be useful. But I'm still playing with this. It would be really interesting to be able to use it maybe just for some parts of the world. But to illustrate that a little more closely, I collected the data from PSK Reporter for, I think this is like 18 hours, and did kind of a heat map of the number of data points for the number of spots that have their control points, which is kind of like the midpoint of the path at a given location in the world. And again, there's no base map on this, so you have to use your imagination, but you can kind of see North America, South America, Western Europe, Australia, and then a lot. But this is the log scale map. This makes it look, kind of okay. But if you want to plot it on a linear scale instead, this is where the activity is. And this makes it very, very hard. We have literally hundreds of thousands of points giving us data in North America, Western Europe, a little bit in East Asia, and then 90% of the world is black, has very scant data to work off of. So I would like to do something with that, but it's challenging. I don't have any kind of an organized conclusion to this, but I would be happy to entertain any thoughts or questions or go back over any material that people didn't quite catch.
Andrew.
Well, I've got to say, wow.
Seconded.
Yeah, that's pretty impressive, Andrew. Kind of mind-blowing, actually. Yeah, I find myself drawn to the site quite a bit, trying to see what's going on. You're right. This, is there any kind of community where you may be sharing some of these concepts, or any type of like, I know you've collaborated with Dr. Erickson a bit, right? I mean, how frequently does that happen?
So not a ton of one, at least not that I've been able to find. And again, finding that kind of thing is part of the reason why I brought myself to YCCC. But I have talked some with Dr. Frizzell of HamSci and Dr. Erickson, and they're kind of quite busy people. So those are just irregular Zoom chats and emails and things like that, which I don't think anyone has had time to contribute to recently, especially since my daughter showed up.
Congratulations.
Well, congratulations.
Thank you.
How do I get? No.
Yep.
Can you hear me?
Yep.
Yes.
It's great stuff, and you're going to get an occasional collaborator like CT1BOH, but most people are going to look at it and go, huh? So if you could gather some questions that people would like answered, and then show in a tutorial how what you've done can answer those questions. Examples of questions that need answering are, I need all the Southeast Asian multipliers I can get. When should I be on what band for Southeast Asia? How do I do that? Another one would be, I want to go to 20 meters single sideband as soon as I can in the morning before the band opens, but I don't want to be there an hour early. I want to be there 5 minutes early.
Mm-hmm.
Is there a way that you can show when it's time to go to 20 meters so that you can get a spot on the band and not get chased away? So if you could collect some questions like that from people, that might get your work used a lot more than if you just say, here's some wonderful charts, figure out what to do.
Yeah, I do agree.
Andrew,
Yes.
may I ask you a question about slide number 22, please?
One moment. Let me get back to that. Okay, go ahead. That's the map, right?
That's the map, and the high MUFs are brighter colors, hotspots, you might call them, right?
Yeah.
So in trying to understand that, what I want for the longest propagation to anywhere, would I want to be underneath one of those hotspots, or would I want it to be the middle of the path that I want the signal to follow?
In the middle of the path as a rough rule of thumb. It depends how long of a path you are looking at. And there are different models actually, but yeah, the muff over your head is more or less irrelevant. The muff between you and where you're going is what really matters.
Thank you.
But if you're doing NVIS regional, then the critical frequency over your head is very much relevant.
Got it. Appreciate that. Thank you.
Thank you.
Super stuff. Just curious, what do you do for in the real world kind of programming?
I work for Vimeo on video backend stuff, video transcoding infrastructure, basically. So making sure that stuff gets delivered to people and that your video playback doesn't buffer and lag and things like that.
So you
ATSC3?
I'm sorry?
ATSC3?
No, this is all over the internet. So Dash and HLS and things of that nature.
Yep.
So what is your development environment hardware?
Completely unrelated to this stuff. Mostly a lot of stuff written in Go and interfacing to libraries like the FFmpeg libraries written in C.
I'm just curious, what type of machine are you developing on? You know.
I have a Linux box. A lot of the people there have Macs.
No, but for this project, for your homework, what are you doing? What are you using?
Yeah. I mean, my laptop that I do the work on is Linux, and the server is a Debian machine that is co-located with a ham in Texas.
Okay.
Andrew, can we contact you for another demonstration for not a presentation for my local club?
Yes, you're like as I kind of mentioned, my time availability is pretty spotty, but you are absolutely welcome to ask and I will work with you.
Thank you very much. And yeah, we understand we're probably way at the bottom of a long list of people, so don't worry about that. I'll just send you my contact information.
It's not even that. It's not such a long list. It's just an even shorter ability to actually take time.
No problem. And that's great. Thank you.
No, thank you.
Is the API described anywhere? I saw that Matt has a question about the API, and I just tried to go to prop.kc2g.com/API, and that also gives a server error. So
not properly, because nothing in it is quite up to that standard of ready for public consumption. But I'm willing to answer questions about it, and I wrote up a summary which I sent to N1MM and I think also to you, Mike, and I would be willing to share that with other people.
Okay, I'll see if you and I traded some email early,
like a good year ago, probably.
Yeah, so I'll see if I can find that, but yeah, I'd be interested in seeing what it is.
Because I definitely, you know, I intend for this to all be in the spirit of open access, and it's just a case of not spending my time documenting things that no one is using that aren't set in stone yet. I might as well, you know, keep changing them while I still have the chance.
Yeah.
Any other questions?
Yeah. Have you noticed any things that when you're looking at the results of your maps, how do they correlate with your observations of actual conditions on the air?
Sometimes quite well, sometimes not so well. One thing that I was doing while I was trying to tune up the ray tracing algorithm was I would actually look at the PSK reporter spots from DP0 GVN in Antarctica, who has a great multi-band receiver setup and just is listening to the entire world's FT8. And doing my best to get things to line up in that way. I'd say it's reasonably good. There's certainly lots of variation. And I seem to predict a little bit low in the sense that it's more often that there is an opening that my map doesn't indicate than that the map says that there's an opening, but it's not there.
And have you noticed, I mean, it's probably not enough time to make any generalization, but I guess it'll be interesting to see how things progress as the sunspot cycle goes through a few years.
It's been interestingly visible. Hold on one second. Let me pop back into screen share for a second. If we zoom this out to 1 year, there's quite a lot of noise on the graph, but you can see around last Thanksgiving, anyone who was on the air instead of eating turkey around that time remembers that was one of the first times when we said, oh, wow, you know, cycle 25 is really starting to do something. And then a couple of peaks earlier this year, and then the past couple of weeks, and even the past couple of days actually set an all-time high in my effective SFI number, which is cool because it does seem to agree with people's experience to some degree. And it also proves that you know, the correlation is not perfect with either with sunspots or with real SFI. So it's, you know, 10.7 centimeters is not actually what drives the ionosphere. It's just a convenient number that we can measure. And I happen to be with a group operating N2J on September 18th for New Jersey QSO party and doing a Parks on the Air. And that was absolutely the worst day of the past month. And yeah, the numbers here agree with that, which I just thought was funny.
You said that your predictions tend to be a little pessimistic. I've seen propagation tables from years and years ago that were based on 100 watts or a kilowatt or a triband or whatever. If you could put a knob on there to let people make them more optimistic, if they have better stations, or just more optimistic so that they don't miss openings that they would miss if they were looking at a pessimistic prediction, I think it benefits everyone to have people trying for openings that don't happen than it is to have them miss openings that did happen. Yeah,
I do agree. And something that's been pointed out by a few people recently is that you know, any kind of tables that were compiled in the 60s were not made with FT8 in mind. And so if your question is, can I make an FT8 contact to this place, then definitely you need a model that is going to be more optimistic than the established ones, because sometimes FT8 can work a miracle or two.
A contest can work a miracle or two because there's people on and it'll show openings that people didn't realize were there.
Excellent. All right, guys, why don't we wrap up this discussion at this point? You all know how to reach Andrew now. You're familiar with him. Check out his site. It's really cool. And keep an eye on the new developments.
Thank you.
Thank you.
Thank
Thank
you
you,
very much
Andrew.
for
That was
having me.
excellent. That's really
Thank
This
you.
was
outstanding.
awesome. Thanks, Andrew.
Thank you.